Good afternoon. Welcome. I think we will start now, and maybe some other attendees will join in the meantime. Welcome to the first stakeholder workshop of the Modeling and Simulation project, which is being hosted by EASA and the Zurich University of Applied Sciences. Next slide, please. Just a quick introduction of the colleagues around the table. On EASA side, you have Laurent Pinsard, which is a technical lead for the project, Elena Garcia Sanchez, our lead expert, and myself as project manager. And from the side of the Zurich University of Applied Sciences, we have Marcello Righi, technical lead, Andrea Pedrioli, expert, and online Pierluigi Capone as the project manager.
Thank you very much.
Slide, please. A few housekeeping items. We welcome all of your questions, feedback, input, and we have reserved the last hour of the workshop for this. We will not be monitoring the chat function on WebEx, so we will ask you to put all your questions in Slido. You can do so during the presentation. And then if you have additional questions, please also use the raise your hand function. To access Slido, you have two easy ways of doing it. You can scan the QR code that you can see on the screen right now, and that will be available throughout all of the presentation. Or you can go to slido.com and enter #modelc. In both cases, you can then log in with just your name or a nickname, and you'll have access to the Slido, and we'll be able to see your questions. And I will now hand over to Laurent Pinsard, technical lead, for a short background and rationale of the project.
So first, we should remind you that modelization and simulation is a part of the EASA research activity program. And the objective of this EASA research is to explore methodology to determine loads on eVTOL. Why did we have selected eVTOL? In fact, eVTOL incorporates already lots of unique characteristics, like several rotors, which develop thrust and lift. We have also a complex aerodynamic with rotor interaction. We have a fly-by-wire. We have a fly condition, which are also unique, like hovering forward or transition phase. And more particular, we have also a more demanding requirement for certification, like a rotor burst with a cascading failure scenario. So for all these reasons, EASA considers that eVTOL are a very good candidate to explore the load, the complexity of the loads. And up to now, the conventional approach selected for loads determination is the development of a complex CFD and a flight test campaign, instrumented flight test campaign with correlation. So we know all that CFD is extremely time-consuming and requests to be correlated. So considering the complexity of the eVTOL configuration, is there is any alternative to determine with a simplified process to determine the loads on eVTOL? And it is exactly what we want to do with this digital twin investigation is, can the progress made in machine learning, artificial intelligence or data fusion offer this simplified approach? And starting from a simplified model, a loading model condition, is it possible to train or to develop a more reliable and sophisticated model with the help of machine learning? And how far can we go to reproduce or simulate a complex loading condition with this approach? And is this approach also accessible to applicants who do not have a specific skill or expertise in artificial intelligence? Can we also propose a methodology to assist the applicant in this approach, a step-by-step approach? And eventually, how this approach can be estimated reliable enough for certification, for future eVTOL certification? These are all part of the question we want to answer, with EASA digital twin research. Thank you. I don't know if Elena wants to add something on this.
No, it's also to mention failure cases, that there is a complexity of failures of individual rotors, how it can affect the others.
Okay, and so thank you, Lauren, for your introduction on the project. My name is Andrea Pedrioli. I'm part of the Zurich University of Applied Science, and then one of the experts of the Model SI project. I will spend a few minutes about the project goals and plan and state-of-the-art topics. The objectives and the expected outcome is, as Lauren said, it's about the digital twin. We are going to explore different methodologies that will give us some flight load envelopes and distributions on different eVTOL designs, something maybe exotic with some various numbers of propellers, with different control laws, flight regimes. We'll try to explore the whole flight envelope, if possible. In, as well as Elena mentioned, in failure condition or degraded conditions, and the different stages of development life cycles. In parallel with this, we will support the aviation guidelines changes, so where we should adapt the certification activities to introduce these new technologies, this new digital twin to help the certification. Regarding the research topics, mainly can be divided in four: multi-fidelity modeling of aerodynamic structures, rotors, and control systems. We'll spend some time later on more detail. The second one, it's that's the broadest one. It's machine learning. We will explore different Gaussian process, neural networks, to leverage data fusion, to merge low and high fidelity methods together. And with this, we will explore the design space for optimization. The case study, the project itself, it will be based on a case study. We are going to define some quantities of the interest. We'll show you later. Then we will build a low fidelity model, which will be our initial physics-based model. Then we will pass to we will increase the level passing to an high fidelity model, and with that we will build the first multi-fidelity surrogate model that will be corrected with some real experimental data, so with flight testing. And at the end, we will assess the uncertainties that the models brings. The quantities of interest are divided mainly in three categories. One is the from, let's say, a maneuver condition. The other one is in turbulent condition. Then it depends on the eVTOL status, so if it's a failure or not, if it's nominal or failure, and then the eVTOL mode, so if it's in helicopter, or airplane, or transition. We will focus mainly on this quantities of interest in detail, which are internal steady-state loads on basically the main vehicle, then the total aerodynamics, forces and moments, and the flight dynamics in trim conditions for the maneuver operational environment case. In turbulent gust, we will more focus on unsteady responses subjected to different cases like altitude hold, or a different dynamic rotor's angular speed, or subjected to the work dynamics of the nacelles, and as well flight dynamics response. Starting from here, I will give the words to my colleague.
Good. So, ladies and gentlemen, good afternoon. I will try to look towards the camera and towards the people here and see what I can do. And my name is Marcello Righi. I'm a professor at Zurich University of Applied Sciences, and I'm also a lecturer at ETH Zurich. I also work as a CVE, compliance verification engineer, for the Swiss company, Swiss aircraft developer Pilatus, and been involved in this project from the beginning. So I will try to walk you through our methods, tools, ideas, and as Joanna pointed out right at the beginning, we'll be happy and grateful for every contribution you would like to provide us with. And we've planned this project with some ideas, and again, if you can prove, if you can learn something out of our ideas, then we're happy. If you disagree, or if you have better ideas, or better ideas, then we are really even happier if you let us know. And again, so our ideas are based on it's multi-fidelity, and we exploit data fusion to generate and develop multi-fidelity model of a generic or multi, or in the case of project, or a specific eVTOL, so depending on case studies or case study. And I will this slide just to introduce our idea, if you wish, of a low fidelity model. And we believe when we say low fidelity, it is physics based, and it is something that runs quickly or relatively quickly, meaning something between less than a second on a laptop to maybe a few minutes on a more powerful desktop computer. But in practice, there's a tool which allows us to explore the entire flight envelope of a vehicle in a reasonable time. So it's not it's not CFD. And in our view, a number of commercial codes, maybe some of you are familiar with Camera JA, Camera 2, or for as far as rotor technologies is concerned. Maybe some of you are familiar with the various programs developed or sold, offered by the American company Zona Tech. They all fall in this category of low fidelity. They don't have CFD. They can interact with CFD, but they don't have itself. They don't have online CFD. So this is our sort of rough definition. We'll go through the different let's say areas, and again, these are our ideas. If you believe that these definitions are not correct, not suitable, obsolete, or something like that, please let us know, and we'll be happy to update our slides. And again, there is no one right solution. This is the way we interpret it, and we'll put it on slides. So in our view, structure dynamics, the structure can be modeled using FEM. So in the 90s, for those of you who do have recollection of those years, there was a stick model. So a FEM model built with beam elements. And let's say something 100, 200, 300 degrees of freedom in total for wing, fuselage, and tailplanes. So something which nowadays on our hardware is calculates a steady solution in a few seconds. And another option could be RITS, or RITS-Rayleigh, as it is often referred to. that is even more efficient, even more computationally efficient. If I remember correctly, this the Camel JA, the old one, was based precisely on that. Now, the second area is rotors / propellers, and we have had a number of discussions, and it's been a hot topic in our regular meetings here. And I started saying that I would model it with a prescribed wake and with something as simple as blade element. And then we discussed among ourselves and with Elena and Laurent, and in many cases we had objections here. Say, okay, prescribed wake, are you sure? And well, we'll leave it open. We can use either blade element, we can use voltage lattice, double lattice. There are a number of approaches here. And but in any case, we would like to point out that if low fidelity, it has to be quick. So we don't consider having online safety here. And we might consider blade flexibility. For instance, some modeling using rits for every blade, and we can have the flexible rotor interacting with the flexible structure, multi-blade coordinates. I believe this was the name of the analytical technique, and we can have the low fidelity model can have all these dynamics taken into account, even variable RPM. So all this will be inside the model. And as far as the more conventional aerodynamics is concerned, so the let's say wing aerodynamics, so then a low fidelity typically is DLM, the vortex lattice method, and can be DLM. I personally sometimes still use string theory for a number of reasons. And you can have string theory, you can correct it for the span-wise distribution of lift. And the good thing is that it's unsteady. So you can, well, DLM is unsteady, and you can implement a Theodor's and aerodynamic lag function based model to take aerodynamic instability, unsteadiness into account. You can do this in time or frequency domain. And we have, of course, a flight control embedded in the low fidelity model. This could be as complicated as it needs to be. And we'll see in the high fidelity slide. But that's a little bit also the great advantage of the low fidelity model, that you can really build in everything you need, every component, every subcomponent that you need to, or that you believe is relevant in. And what you have out of this model is, again, it's very quick and allows you to, for instance, to assess, to calculate the dynamic response in the entire flight envelope in a useful time. It's not like pressing a button and coming back 1 week later as you do with CFD. It's something which provides you the entire loads, for instance. Andrea mentioned the quantities of interest, mechanical loads, for instance, for the response to one particular gust, and you have it within minutes, or if not seconds, and in a number of configurations, different configurations, of course. It provides you with steady loads, with response to unsteady pilot's input or gas response, for instance, and it allows you also to propagate uncertainties. So you can decide that your problem has a number of aleatory uncertainties, so quantities you're not sure about, and you can do your analysis a number of times, varying this parameters, and typically this is something you call Monte Carlo, and there are mathematical tools, methods which makes Monte Carlo more effective, such as polynomial case. Just an example. And the other thing you can do with the low fidelity model is the assessment of dynamic stability. So you do it in an entire flight envelope. You do it for the number of configurations you need to do it, and you can determine very, very quickly the dynamic stability, linear stability. So as which means the eigenvalue analysis of the system. So you have your system model, you linearize it if you need to, and the eigenvalues of the system matrix, that give you the piece of information you want to have. So the real part of the eigenvalue is positive, then it's unstable, not positive. No eigenvalue is a positive real part, then system stable. And if you're good enough to have your nonlinearity in your model corrected, then you can even investigate limit cycle oscillations. And so you may even want to go beyond flutter, so inside, if I can use the expression, inside dynamic instabilities. And again, you can do this. You can calculate the uncertainties associated with flutter speed. And again, the whole thing is very, very quick. Now, of course, as that I mentioned right at the beginning, we were talking about low fidelity models. So it's very, very quick. It's complete. It has everything in. It's not perfect. And the physics, and I believe that Laurent mentioned it right at the beginning, the physics is complex here. And so we cannot expect a low fidelity model. We cannot expect VLMs through theory to capture everything that needs to be captured there. So low fidelity is good, some basis, but we need to look into also alongside the low fidelity model, we need to have a high fidelity model. And the high fidelity model, in our view, and again, you feel free to disagree and provide us with your comments, your criticism. We'll be happy and very grateful of that. So we call a high fidelity model a model which is physics based. Sorry, again, and it may have an execution time of up to a number of hours, and maybe some of the participants have direct experience with CFD analysis of these particular vehicles in any or in more than one configuration, and you can testify it takes a long time. So the CFD simulation of one wing with one rotor as actuator disk takes a few hours to converge, and this is probably the simplest option we have here. So again, high fidelity, physics-based, very, very demanding, or let's say demanding, computationally demanding. And it might be limited to steady state, so allows us to calculate a steady state of the response. You can use to calculate flutter speed. You can do that. It takes forever. So those of you who are familiar with that, and you know that one unsteady response is computationally more demanding than one steady state. It is, of course, well known, and you want to track flutter, then you have to carry out a number of unsteady responses, and it all adds up. So the computational demand here can really be very, very high, and why not? We can limit the scope of the high-fidelity model. So I believe you mentioned right at the beginning the interaction between rotors and wing, rotors and wing, and we can have a local, a limited CFD model looking precisely into that, and so we keep the high computational cost within limits. It will still be high, but maybe we can bring the computational time down from 6 months to maybe to a few hours, a few days. Right. So again, our definition. Feel free to disagree. Feel free to propose your solution. And again, we thought, or our idea is structural model is FEM, not a stick model, a complete FEM with different types of models of elements. Sorry, and maybe under a few 100,000 degrees of freedom, maybe 1 million, something like that. And again, nowadays this runs no problem on even on a small laptop computer like this one. And again, many of you maybe have experience with master and abacus, which is probably written with a Q and not with a C, so I apologize. And so you know what I'm talking about. And in some cases, you build your abacus with Q model, and then you reduce it. So you don't do it as a complete master and abacus ANSYS whatever model, but you carry out a model order reduction, modal with a order reduction sometimes. And now, the most important one, the rotors / propellers. Now, I mentioned before, just a minute ago, we can have rotors built or represented in the CFD domain as actuated disk, which is a disk, an idealized disk. We can either have a physical mesh, or if you calculate with overset, Chimera, you can have physical disk mesh inside your standard regular CFD domain, and you apply some source terms into the solution. So you have the thrust coefficient, you have swirl across the rotor. Works well. It's not perfect, as we discussed over the past couple of weeks. It's very, very efficient. So you calculate steady state. It takes a little bit to converge, but it's the computation times is within limits, so it's perfectly acceptable. Okay, not perfect. So I believe that we had some questions from Helene and from Laurent, saying that, well, after all, you see, the physics here is complex. So with the activator disk, we don't see single blades, and I agree. So the activator disk is one of the options, and now moving up in the along the fidelity scale, that you can have a multi-domain. So you can have a rotating domain with a rotor, with a physical rotor in it, and a not rotating domain with fuselage and wings, and there are a number of points in between. So we can do you can envisage, you can plan your high-fidelity modeling in a number of ways. And again, if you have specific experience there, then we'll be very happy to hear from you, and if you any feedback is welcome here. So we have in that respect, this is an area in which we will really welcome feedback from you. And now the regular aerodynamics, so wing and fuselage aerodynamics, so could be CFD, and could be RANS, so Reynolds averaged Navier-Stokes equation. It could be RANS with transition model, if you trust these models, and this can be useful, can be even necessary at low Reynolds. So depending, talking or mentioning or speaking the eVTOL word, now we can picture in our minds their particular configuration. Some of them have a reduced core, so Reynolds number can be low, and if Reynolds number is low, then transition will be an issue. So you can have laminar separation bubbles appearing here and there, and to represent them correctly, then you do need the transition. If again, simulation can be steady, can be unsteady, can be steady state, can be time accurate. If you're not happy with RANS, in some particular cases, in particular with the if you're allowed to keep your model local, then you might even try DDS. I believe that one of the first the image in the second slide, I believe it was something like that. It should have been a detached edge simulation or a delayed detached edge simulation. So numerical techniques with which physically resolve some of the turbulent eddies. So not everything, of course, not the DNS, not a direct numerical simulation, but a portion of the turbulent spectrum, energy spectrum, can be resolved. In some cases, it does enhance the accuracy of the solution. And large eddy simulation might maybe be an option in a very limited special limited model as well. And again, flight control can be made as complicated as we wish. So again, we can do a lot even in the low fidelity counterpart of this, but having the computational power, then we can really have it as we like, and or as realistic as we would like it. And on the other hand, what we expect you can do with a high fidelity model is okay, dynamic response, well, a few points. Unless you do have at your disposal a significant computational power, then you can afford a large number of flat points. You can afford simulating maneuvers, so even a time-accurate response to pilot's input, for instance, or you can simulate a complete gust or the response to a gust encounter in time domain. In most cases, but I believe that even the large manufacturers which have access to virtually unlimited computational time, they tend to limit this analysis, not because they cannot afford it, but because it's not so practical. Again, it is this kind of simulation. You start them on Monday morning, and you have the results maybe over the week or close to the end of the week. So by the time you have the results, you might have forgotten what the settings were, and so it's something people do within limits, I believe. But again, feel free to disagree and provide us your opinion on that. And now we mentioned flutter analysis on a high fidelity model. Difficult. So you can do it. It takes a long time. It takes a lot of computational power, and of course, it takes also a lot of your time. So you don't have to pay only for computers. You also have to pay for people looking at computers and try to make sure that everything runs according to plans. And an option or a possibility we have here, of course, is to carry out use the high fidelity model to train a reducer model. And if done properly, the reducer model retains all the relevant physics, and you can carry out your analysis with that. So typically, flutter analysis is or can be done through a reducer model. So you have a high fidelity model, you generate a number of responses. With the responses, your responses are treated as data, and with the data, you can train a data-driven, or you can obtain a data-driven reducer of the model. With the aerodynamic reducer of the model, you can carry out your flutter analysis, and you can investigate or explore a certain area of the flight envelope. And so we mentioned right at the beginning, and I think Andrea mentioned going through the flow chart, the different blocks and then the flow chart, mentioned the multi-fidelity and data fusion. So again, this is our idea, and we believe, or we know, we've read about that, we have little experience in that, and we believe that multi-fidelity could be a way here. And it means building a multi-fidelity model, or you can call it a surrogate model. And surrogate model is not physics-based, it's data-based, it's data-driven. And it means that in practice, and some of you are surely familiar with that, it means that the low fidelity and the high fidelity models are, so to say, merged into a third model, which is a multi-fidelity model or a surrogate model. And this surrogate model, or the outcome of data fusion of this multi-fidelity entity, is in theory as fast as the low fidelity model, and in theory as accurate as the high fidelity one. So as accurate, not everywhere, of course, but in the relevant points inside the flight envelope. So it is accurate where we need accuracy. And maybe some of you have direct experience in rigging, and so maybe maybe you're more familiar than we are in this activity, and this is often done with on the basis of ghosted processes, and in particular kriging and co-kriging. So I use kriging with the low fidelity, with the points from your low fidelity model, and you develop a second one, a co-kriging. You do co-kriging in order to build your multi-fidelity model. So as our idea, we'll go through a few examples, and hopefully I will be more clear looking at the examples. And before we do that, a few comments about why or what we expect from machine learning. We go right at the end. We go. Well, I will mention the quickly result of a literature survey. And if you do that, if you look at the relevant papers issued in the last couple of years, then machine learning is everywhere. So it's very well known. You don't need to learn it from me. And in this particular project, we believe there are some areas where machine learning is useful. Again, we just mentioned one slide back, data fusion, and looks like ghosting processes can be exploited for that. And ghosting processes are often classified as machine learning. You can do the same with neural networks. So you can, if you're unhappy with regular ghosting processes, you can tailor-make your neural network. It takes a little bit more time. It takes more preparation. You have to be familiar with that, but you can really drive the accuracy or maybe the uncertainty computation to the level you want it to be. So, example, data fusion, either GP or your neural network, or if you do this with a different approach, please let us know. We'll be most grateful. And on top of that, the machine learning is very useful with the high fidelity data. So high fidelity models tend to generate lots and lots of data, numbers, and sometimes the amount of data is overwhelming, and it takes really a long time to look into it and try to identify, well, what is the vortex? Is this vortex relevant? Is this vortex important in characterizing the interaction between the rotor and the neighboring rotor, between the rotor and the wing? And we have a number of examples of algorithms which can be used to capture patterns inside, for instance, CFD solution. And again, this is what you use machine learning for. This is what you use in particular neural networks to identify patterns and to extract physical characteristics. And this is not the peculiarity of machine learning. Now there are surely people here connected here who are familiar with PLD, proper thermal decomposition of DMD. These algorithms are not machine learning. They've been around for a number of years, and they're very effective in identifying patterns inside, for instance, CFD solutions or even wind tunnel solutions or measurements. And again, they're still very valuable and very useful. Machine learning can be a good alternative, seeing that people start replacing POD with this encoder-decoder architecture, neural networks. And instead of extracting patterns in the shape of modes, then people extract patterns with the help of for instance, convolutional neural networks. So almost quote unquote graphically. And in some cases it works very well. So we believe this is a good point. So this is something you can which is very useful and something you can do with machine learning. And now on top of that, and I believe I should mention this comment. There are a number of software packages used to extract to exploit these algorithms, and I've written here a number of them: TensorFlow and PyTorch, scikit-learn, and GPy, GPFlow. And these software packages are available, are publicly available, and they're not being developed for certification of aircraft. They are available to the general public, and they've been exploited by a number of engineering fields. So the degree of validation of this software is very, very high, and numerically they're very efficient. And it means that you can rely on this on the software. It's incredibly powerful, and I don't want to advertise for anyone. So they're probably more than that, and I apologize if you believe that I'm mentioning these names. I explicitly refer to the company behind it. Well, some are open source, but TensorFlow and PyTorch. So we know they're developed by specific companies. Well, I don't want to do that, but I want to focus on or to point out that they're available. They're very well. They're very nice. They work very well, and they make your work so much easier. So in this data fusion thing was done even 30 years ago, 40 years ago, but not with such a reliable software. That is, I wouldn't say it's a game changer, but it surely is a big help. Right, so I believe we can go through the examples now, and we are more or less on time, on schedule. Let's see. Right, so I'm proposing here 3 examples. The examples are not eVTOL, or one, okay, they're not eVTOL. The third one has some commonalities with eVTOL, but they come from different studies, different types of analysis. The first one is the wind tunnel model. It's due to Professor Ravet from Technion. It is a little straight wing span of 55 centimeters, a chord of 100 millimeters, and it flutters. It's a flutter model. It flutters at between 30 and 50 meters per second, which translates to a relatively low Reynolds number at sea level, please. And it's something like 300,000 Reynolds. And so it's not trivial. It's not trivial because this wind tunnel model bends a lot. Well, you will see in the next slide. And the challenge here is flutter speed. So we have to detect flutter speed. It's one of the test cases in the aeroelastic prediction workshop. So again, detecting flutter speed requires a number of calculations. And so you do it on with a low fidelity. You don't do it with CFD. At the same time, the physics is complex here. So low Reynolds number and large geometric or large displacements. And so you might want to check out with CFD if your low fidelity VLM strip theory, whatever it is, if your low fidelity is doing right. Now, just to give you an idea, I believe this, let me see if it starts. This is static wind tunnel in ETH Zurich. Gives you an idea of the static displacement. It wasn't even too fast, it's 30 meters per second, something like that. And you see the displacement's really, really large. So again, it's not too difficult. So VLM, even strip theory is not too wrong here. But I mean, it's not trivial. And sorry. Wait a second. Right. And the nice thing is that in wind tunnel you can characterize the steady response and the unsteady. You can relatively easily see the living cycle. So as in a given area for a given speed, and the response becomes unsteady, the system becomes unsteady, and you see you can identify flutter speed, and luckily there are some non-linearity, so it does not explode, breaking the wind tunnel and causing large damages, but it evolves into a living stabilization. Was there a question or anything we need to stop?
No, there are a few questions.
Okay.
So if you have any for the examples, please drop it in Slido. There is the QR code.
Yeah. Okay.
Over here,
Yeah.
by the way, you can access easily.
Good. Good. Yeah, I thought I saw. But anyway, just as if there is anything urgent, just stop now. And so again, any to identify flatter speed here. Move to the next one. Good. And so again, we need a low fidelity to carry out a flatter analysis, but we would like to check out the accuracy of against a high fidelity. And this is what we did here. You see this is just an example extracted from another model. It is the curve shows the overall the lift coefficient of the whole model as a function of the angle of attack. And we compare here the low fidelity strip theory, unfortunately. In that case, the black dots with CFD, and CFD was with the transitional model and so on and so forth. And it is the blue line CFD, and maybe those of you who are into these things can appreciate the fact that at the low angle of attack, we have a change in slope. It's typical when a laminar separation bubble appears. And if we want to merge the two models together, so building a circuit model which inherits the behavior of the low fidelity model and at the same time matches the high fidelity points, then GP, the co-creating gives us this red line, and see is right on top of the high fidelity. So this was easy, and but it's an example. We also have some uncertainty, one sigma plus one sigma, and it's very small. So if we apply that data fusion to this particular curve, then it works very well. Now let's see another aspect. Now, this picture is relatively young, so I hope it is correct in every detail, and I hope it's understandable. Now we have again, it's another comparison we did between you see the red dots here. The red dots are CFD points, and it's represented on a three-dimensional chart. We have on this y-axis we have the deflection. So it's first of all, it shows lift coefficient of a number of sections. We cut the model into 16 segments, and so we represent here the lift coefficient on the z-axis, and we do it for different level of deflection. So deflection at the tip, and on the x-axis here we have the section number, which means a coordinate along the span. So we represent lift coefficient for 16 segments. So we cut the model across and calculate with the strip theory and with CFD the lift coefficient. And the red dots are CFD, and you see zero deflection. You see the points here, it's more or less elliptic, or it's not too different from the typical span-wise distribution. And if you look at the opposite curve, the one at the highest deflection, degree of deflection, then distribution is very different. The root is the root of the wing is loaded. It's much more loaded. The tip is much less loaded. And you see that the low fidelity of the surface with different colors is the surrogate model. So it's a multi-fidelity model. It inherits the behavior, the patterns of those of the low fidelity model, for which we can calculate many points, and at the same time it matches CFD. So, and this is a typical example in which data fusion is useful. And If you do that, you can carry out your flutter analysis, exploiting the speed of the low fidelity model and the accuracy. You just obtain matching the CF points. And doing that, again, this will waste 10 seconds here. This is the final result. So you have a chart here with wind tunnel speed, airspeed, sorry, and the angle of attack of the route. And you see the purple area is the unstable area. So where the model becomes unstable and shows this living cycle. And the white area is the stable region. The red symbols refer to experiment. This is my solution. The other people in the aeroelastic prediction workshop on similar methods were a little bit more accurate than I was. I don't complain. It can be improved, but it's just to show to you that they are calculating all these points takes many calculations for many. We have to run our model many times, and it has to be quick. It has to be quick. It has to be accurate at the same time. And by doing that, we try to have both advantages. Now, of course, you can claim after all is not so accurate, and if you do, it will be a fair criticism. But again, models can be implemented and can achieve a higher level of accuracy. Now, okay, we have the living cycle again. I want to move to the next one. Now, again, example number 2 is very quick. Again, from the elastic prediction workshop, this is again yet another wind tunnel model. It is a straight wing, and it's fluid transonic. And aerodynamics can become strongly nonlinear. And again, the aim of the exercise calculate or set flutter speed for a number of in a range of Mach number and angles of attack. So we can consider this Mach number angle of attack plane, and we can as the exercise we try to determine the stability and stability areas. And again, we do it numerically, so we don't have a low and high fidelity models here. We have a numerical model, which is actually high fidelity, and we compare it where we carry out a data fusion exercise against experimental data. And so we don't have strict theory here, be out of place. We have runs, so CFD against the experiment. And experimental data are very few. So there are really a few points available. It's very expensive, and so the flutter experiments were carried out in the 90s, and we have a number of points, only a few points, 5, 6, some points, something like that. So this is our okay. So you see the plane, the x and y axis, Mach number and angle of attack. So Mach number between 7.4 and 8.4, and the angle of attack is 0 and 5 degrees. And you see the z-axis is the one about the flutter dynamic pressure. As it's in pound per square feet, the whole workshop was like that. So we get the American units. And so you see the surface is this is what our numerical analysis gives, and it gives a relatively irregular surface at low Mach, or say below 878, something like that, and low angle of attack. If you increase both Mach number and angle of attack, then you see the curve, the surface becomes bumpy. So you have hills and you have valleys, and it becomes extremely irregular. And so we immediately notice that our approach is not accurate everywhere. And we compare it with a few experimental data available. And if you do that, and if we apply data fusion, then we obtain something like that. So the scaling of the z-axis has changed. Now it's 200, the maximum is 200. It used to be 400 or 350, something like that. And we see now the surface, the regular portion of the surface has remained more or less unchanged. And it matches how many? 1, 2, 3, 4 experimental data. The thread dots on at zero angle, at angle of attack 0 are experimental points, and they are captured very well, or relatively well. Now, there are other points which are partially hidden, I believe, at higher angle of attack and higher Mach number. And they are much lower than the predicted value. So our data fusion process brings the whole, let's say, you remember that the hilly portion of the surface, it's almost bent downwards in order to improve the matching with the experimental points. So again, this is the prediction, this one here, and data fusion modifies the or more strongly affects the irregular region, and it makes something like that. Now, this is a bit of an extreme case in which data fusion, the surrogate model is very, very different from the low fidelity model. And we mentioned right at the beginning the uncertainty associated with that. It's not shown here. We can carry out these processes in such a way that we not only have the surrogate model, we also have an assessment of the uncertainties associated with the process. And in that case, again, it's not shown here, unfortunately, but it will show a very high uncertainty in that the data fusion process would inform us that this is our best solution, the algorithm can do, but pay attention, there is uncertainty in matching such different data. And again, it's a valuable example in that it shows the changes from low fidelity surface to a multi-fidelity surface or surrogate model. Now, the third example is about a vehicle and the XB15, for which a quantity of data is available, publicly available, such as the report indicated here. And so we use something completely different. We've been practicing with that Stanford University program, aircraft design. It's I believe this says the Spanish word has some meaning, ZHAW, but I know these people call it ZHAW, so I will keep their pronunciation of the word. Is Professor Alonso group behind this? The same people who developed, or same group, same professor who develops C2. In case you're familiar with it, and it's very well done. It's not so easy to learn. There are different fidelity levels, no CFD, but among the low fidelity there are different fidelity levels, and so we built a surrogate model for. We built a low fidelity model for the XA15, and we tried to calibrate it as good as we could, and in the end, we have some predictions. We focused on power required, and we focused on the attitude of the vehicle in airplane mode. So we only looked so far. We only looked at the airplane mode, and we tried to compare it with the available flight test data. And this is extremely fresh, and so this is the basis here is due to the extra effort by our colleagues. So our colleague Fourier and our colleague Gabriel, they did really incredible job tonight. And so what we have here is we have points. So this is what we get. We have points from low fidelity, the one marked as ZHAW, and the other one marked as experimental. And you have on the left-hand side, you have power required per rotor. On the right-hand side, we have the pitch attached to the vehicle. And again, it varies with the airspeed. We have two parameters here. We have the altitude and airspeed. You see, these two quantities tend to vary a lot with airspeed, a little bit with altitude. And you see, the points are not too far from each other. And we can use data fusion here. Again, it was not easy, but it was possible. So again, very young results. And we see on the left-hand side that the power required per rotor XV15 airplane mode, so I stress on the mode, on airplane mode. On the right-hand side, the vehicle pitch attitude. And you see the black dots are the flight test data from the report, 1990s or 80s, or whatever it is. And the colored surface is the multi-fidelity model, or the multi-fidelity surface, I beg your pardon. And it means that with a relatively inexpensive tool like this ZHAW, you can reproduce and exploiting the flight test data which is available, publicly available, you can build a model, or you can have a multi-fidelity model, which is very quick to run and is accurate enough to match the flight test data. Now, I believe it's a few minutes past 3. We have the literature after this. We can either stop here for a few minutes, and we'll start in a few minutes with literature, and or we can go through literature. It will take maybe another 10 minutes, so we can stop here. I don't know. What do you think?
We can maybe just make a short 5-minute break now, and we can be here back at 3:07 promptly. Good. And we continue. And in the meantime, if there are more questions, the participants can also put them on Slido.
Thank you very much. So we're back in a few minutes. So
welcome back. I hope you managed to have a short but good break, perhaps a coffee. I'm going to hand over back to Marcello.
Good. Thank you very much. And I noticed there are a few questions, so we can now the slides left are those about the literature survey, and will be relatively quick. And then we have a few questions already in, so we can go through them after completing the few slides left, and then we'll probably have time for discussion if you wish to participate. And we have in the meantime, we have collected our other questions from different sources, and we can also go through that. Right. So going back to our slides, good. So right at the beginning, is January, February, went through a review of the available literature, and it became immediately evident that looking at the last couple of years, there are three areas in which the number of papers published is large and increasing. So typically, namely, one of these areas is eVTOL itself. So there are many publications on new configurations and how you would exploit these configurations. The second area is the famous or infamous digitalization topic, in particular papers dealing with the relevance of the suitability of more simulation, more digital process in aircraft design and certification, with maybe a more and more emphasis on, well, I would say emphasis on both design and certification. And the third topic is how is machine learning applied to aircraft design, or applied in particular to aircraft design and to modeling, and how it can improve modeling, how it can make modeling more accurate, more quick, more effective, or whatever advantage it can provide you with. And now, again, briefly, these slides I collected made some statistical, if you wish, data about the content of the SciTech AIAA conference, SciTech conference, 2023, held in January, this January, so about 27 January 2023, and simply because it was easy And SciTech, inside we have a few thousands contributions, and they are all collected the same way. They're very uniform, and it's very easy to search. Now you can do the same with the website of the various publishers. Of course, you can do Google Scholar, but within the same conference, it's even easier and faster. And the great advantage is that the contributions are more or less homogeneous, and they come from engineering, mostly from engineering. So again, there is a certain uniformity among papers. And so looking for eVTOL, we have about 120 papers out of a total of a few thousand. So not too much, but still, it's not a little number. And again, many papers deal with design and meaning optimization, and others. A number of them were focusing directly on aeroacoustics. So this aeroacoustics, and then eVTOL is also a big one. And some others were focusing on on what to do with eVTOL. So how eVTOL can change the way we fly, we move goods and people, and also how we can let them fly autonomously, and how this type of flight can be certified. Sorry. And in most cases, people do that on the basis of low-fidelity modeling. There are a few examples on high-fidelity. There is one nice example of optimization based on CFD with actuated disks. And some of them have, again, high-fidelity, some have multi-fidelity models. But again, in SciTech, year after year, you see this number increasing every year. Now, digitalization in certification process. Now, we didn't see much actually at the SciTech here, but I will mention three dots, or three bullet points. Sorry. And one is this NASA technical report 2021. And the other one is the AA white paper on digital twin. Yeah, I believe it is 2021, and I don't know why I forgot to add the date. So I apologize for this. It's probably 22, but again, I apologize for the missing data. And the other bullet point is not a publication; is a reference to this EU project, ROCS, I believe the acronym is, and I believe that our colleague is online, so he's
Yes, they are.
He's welcome to share his point of view, and he's welcome to offer his the way he or they see the role of digitalization in aircraft design and certification. And again, it's meaningful to have a EU project funded on this topic. It testifies that the relevance of this type of analysis. And the last one is about the role played in machine learning. And again, there are 1 million papers being written every day, and limited, or if you limit the scope of our analysis to SciTech 23, we have about 300, and we have a number of sessions devoted to machine learning. So SciTech is huge. Conference, you have N or hundreds, maybe, of parallel sessions, and so many sessions. So the week, and 6 of them were devoted directly, so they directly mentioned machine learning. And we have papers on data fusion, 23. We have papers on surrogate modeling, 130, and we have papers on multi-fidelity, about 130. So I attended the conference, and I attended a number of them. Many of them are really high level, so I learned a lot. And as we mentioned the other day, the community working on these exercises is making, in my view, huge progress. they become better and better, and also they have developed their jargon, and so if you come into the room and you listen to them, it takes a while before you really understand what they do, but they do those things, and really impressive. Now, if you look more carefully into the status, many cases people exploit GP or gas and processes to, for instance, for data fusion, as I said a number of times. But in many cases, people they develop their own neural networks. So again, you can exploit TensorFlow, PyTorch. You can exploit other packages. You can use MATLAB, of course, and all these things are also or partially at least available within MATLAB, and you can build your own network. You can exploit this software to generate, to invent your own neural network, which captures the physics you're interested in. And again, in general, the motivation, the rationale for machine learning is that we use it to capture nonlinear. This is the big advantage, the big added value of machine learning. So now there were a few questions here about the suitability or the meaning of having machine learning in a project, and the rationale. Again, as our point of view, we can be wrong. Rationale is that machine learning is powerful in capturing nonlinear. And if you're able to capture nonlinearity and package them nicely into a mathematical model which runs quickly, then you have a high accuracy, or you have complex physics, nonlinear physics, which runs quickly. So that's the idea. So you exploit CFD, you exploit your measurements, you exploit wind tunnel, flight test, whatever. And with all this data, you exploit machine learning, which again is available conveniently in a number of packages. You exploit machine learning to capture the relevant physics from this data and make it available to you for further design, certification process, or whatever, in a very convenient form. And is it the end?
Yeah.
Good. So we reached the end of our slides, and I believe if I haven't forgotten anything, we can maybe look into the questions.
I think just before to move to the question, we can summarize that from this presentation and the EASA understanding of these activities is, first we can have some questions. We have questions, and the first one is machine learning approach is feasible and achievable, means to educate a simplified model to reach to the level of a high fidelity model. Is this achievable or feasible? It seems that according to your presentation, it should be.
It is feasible.
The
question is the cost of this.
The one question we can have from your presentation at EASA level again is why this machine learning approach should be selected for eVTOL loads determination. So you mentioned that it's quicker, cheaper, and it provides a comparable result from a high fidelity model. But the next question is how much effort or energy you should put in the system to reach this, and at the moment it's a question mark. And in fact, also is what is the process to use artificial intelligence, and how an applicant can succeed to do that. Is it achievable at the applicant level? It's part of the question we still have.
That is the question. So first part of the question, why is it relevant in eVTOL design or certification analysis, whatever? And I believe it is because of the complexity of physics. You have that picture on the top right of the slide showing the mass multiplicity or the Q factor or whatever. It shows the complexity of the physics. You have a number of interactions between different units, and again, I believe it is meaningful. It will be meaningful precisely because of the complex physics. the first part of the question. And again, feel free to use it. And the second part of the question is definitely more difficult. How, in practice, how do you go about it, and how demanding it is? My personal impression is that it can be demanding. It can be very demanding. So if you make a comparison, you buy or you rent a CFD package, you learn how to make your grids, and then provided you have sufficient computing power, you press the button and you come back. Several weeks later, you have your results, and that's it. You have the technology or the knowledge, the experience you need in order to exploit properly machine learning is that in my view, it's not trivial. So an absolute beginner or someone who's not familiar with machine learning can have a hard time in starting. Yeah, I believe there is a threshold to enter this technology, which is it's not little. And there are some caveats, though. The software is available. So for instance, to make an example, you can start using machine learning to solve a simpler problem, not this one, not data fusion, but simply build a surrogate model out of some data. You can learn very, very quickly to do that. And I believe some of our colleagues are online, and we started using TensorFlow or whatever 3 years back, and you can get started very, very quickly. So you can build your own neural networks in a relatively short time, and this works very well. So at least students, graduate students, doctoral students. So the colleagues who helped me realize this, they learned very, very quickly. So inside academia and research institutions, this goes very well. And this goes increasingly well because the number of people familiar with the process increases as time goes by. Now, your question concerns maybe someone who is involved in designing a vehicle, eVTOL, for instance. These people are not necessarily familiar with machine learning, and they might be engineers or experienced engineers. They might be familiar with low-fidelity techniques. They might be familiar with CFD, but not with machine learning. And you can exploit machine learning also to look inside your flow patterns, for instance. Also beside data fusion. And the answer, yes, I agree. It is difficult. Alone, if you have this, my personal impression, if you're alone and if you want to start looking into machine learning, it can be difficult. It is difficult. So it takes some time. You have to take some time to it. The good thing is that the opportunities you have to learn or to have assistance support from universities, research centers, numerous. The people companies involved in development of eVTOL, I believe our communities were small, so everyone knows everyone else. And, you can relatively easily come in contact with people knowledgeable with this. Not ourselves, of course, but this familiarity with the process is available throughout the universities. I would say in Europe, in America, and in other countries as well. So you can be supported, in my view, relatively easy. And in EU projects, there are systematically small companies, and they have the opportunities to learn. Now, there are also my standpoint might be maybe too much influenced by Switzerland, but I'm sure there are also in Germany. There are some national programs which allow research institution or university to support companies in applied research, and there are similar programs throughout Europe, I believe, and this is also a way you can exploit it to start moving into this technology. And but it does require an investment at the beginning, and the investment is not small. Now, I perfectly agree, and even people like ourselves who who allow themselves to speak about machine learning, we still have to learn. So we still have to become more and more familiar with these processes. The real expert, very few in this fields.
Maybe we can start.
Yeah.
We can start having a look at the online questions. And one of those that took particular attention is about Yari Tauria. Sorry for the pronunciation if it was wrong. I'm sure it was. And the question is about validation of machine learning tools. So what consideration have been given or activities performed with regards to validation of ML tools used in the study?
And certified.
Absolutely.
That's a good one.
Yeah, absolutely. We can say that the tools, the methods themselves, so the software you use is benefits from a high level of validation. Where was it?
We can even.
No, it was here. I remember it was before the examples. Yeah, it was here. The tools themselves are absolutely reliable, in my view. So you can trust all this. You can trust MATLAB. I apologize. I didn't write MATLAB in there, but the tools themselves are absolutely reliable, in my view. They can count. You can count them on many users every day. So the tools themselves are very they benefit from a high degree of validation. The validation of how the tools are applied here, that's a completely different matter. And I agree with you that this is one of the points we would like to touch in this project. This is precisely the most important point we would like to explore in this project. So we have a complex physical problem. We have very good tools, and we would like to apply these very good tools to the solution of to the solution of the problem at hand. And this is precisely the challenge, the gamble here. So we would like to show that it works, that the tools are very good and they can be applied, and the project itself. So this project itself will be a preliminary or initial validation, or will provide hopefully some elements of validation. But so far, as of today, I personally have no evidence yet. So if you believe that the process we talk about not validated and they will not work, and that according to your personal experience they are not suitable, then maybe you're right. Hopefully not, but it is precisely the question we would like to ask. Then feel free to disagree, of course.
Okay. Then the second one is from a person that we know pretty well, from Professor Quaranta of Polymy, and he's asking, how do you deal with cases that are beyond your flight test envelope? And if you can you still use your trained model that fuses low fidelity and high fidelity models to extrapolate?
Yeah, it's a good one. Thank you very much for the question. And I'm sure that Giuseppe already knows the answer. And of course it cannot. So it depends. The surrogate model you have, the multi-fidelity model, is of course as good as the data you use to train the multi-fidelity model. So if you exclusively use flight points inside the flight envelope, then you cannot expect your surrogate model to also provide answers or reliable answers outside of the flight envelope. And it does, though, it does provide a measure of the uncertainty. So if the point outside of the flight envelope you're interested in it needs or requires a quote-unquote extrapolation, then the data response, the response to the model would come in many cases also with a measure of the uncertainty. And in some cases, this uncertainty is the key to answer the question. In some cases, if the quantity of interest that you're looking for as a smooth behavior, then you can extrapolate, and the uncertainty, in this case, the epistemic uncertainty, will be limited. If you would like to explore the flutter speed outside of the range we showed here. Wait, no, it's sample set after a later. Where is it? Yeah, if you want to interrogate the model about flutter speed at Mach number higher than 0.84 and at angle of attack of 5, then your response will be associated with a high uncertainty. So it really depends on the data, and I believe it's a question of common sense in that you look just to stay on this example, you want to extrapolate the flutter speed or dynamic pressure here at angle of attack -1 and low Mach number 0.74. You can do it, and the associated uncertainty will be limited. You do it on the other side, and it doesn't work. I believe the key here is, and I believe you touch on you must be touching on this point in your ROCS project. Is the key is probably to carry out your analysis or your low fidelity, high fidelity, whatever analysis in a sufficient number of points, even outside of the flight envelope. And it's not an easy question to answer. It goes again on the limits of the validity of the approach we propose. Not easy to answer. So I can say it depends on the problem. It is a question of engineering judgment, and it is also a matter of how many points you select, right, or at the onset in the planning phase. I would say again, feel free to disagree.
Thanks, Marcello. Then there is another question from Martin, which is asking, how do you cope with the non-deterministic nature of some machine learning?
Yeah, that's a good one. I don't know. I've always asked myself the question, and in a number of papers you see the analysis carried out a number of times, and in other papers it is summarized with the uncertainty, with the epistemic uncertainty. So you have the your results are proposed and published as mean value and a certain confidence interval. So they are sold, quote unquote, like this. But it's a very good point. So it's one of the things that I believe that we our group and needs to become more familiar with. It's absolutely some of the algorithms are say quote unquote non-deterministic in that you have some random processes and guiding the algorithm. So it's absolutely right. It's one of the things that we would like to know better. Thank you very much.
Thanks again. Then another one from Diari again is asking one appropriate question about what is the driver to add to the simulation. What is the driver to add artificial intelligence to the simulation? He's saying modeling loads and understanding new eVTOL aircraft configuration sounds already challenging in itself.
Yeah, absolutely. the simple, the direct reply here is that if everything goes as planned, machine learning is a support, is a help. And in that, as you said just now, if we become sufficiently familiar with these techniques, then we can capture the physical complexity in a more effective and in a more efficient way. Effective meaning that we can capture the physical complexity, and efficient that in the end the effort is feasible, is acceptable. And again, just an additional comment. Modeling the loads with a low fidelity model is challenging. It's very complex because you have to really understand the physics, and you have to build inside your low fidelity model all the necessary mechanisms able to capture the physics and the nonlinearity. Whereas with the high fidelity modeling, you don't have to what you have to have computational power. And so on one hand, if you had unlimited computational power, you could solve everything by CFD. So I don't know, 100 million computational cells, so you can simulate all gas response in all possible configurations. And again, if you have unlimited CPU power, then you can do that without worrying about complexity. Everything is there. It's like flying almost. And in practice, it's not feasible. On the other hand, as you're correctly right, low fidelity data, it's difficult. It's complex. You have to really understand the physics. You have to really think hard how you build the model. And we believe that machine learning lets us take the best of two worlds. So we limit the effort inside into the low fidelity model, and of course we know it's not accurate, it's not sufficient. And if everything goes well, then we can compensate the insufficient accuracy, extracting it from the high fidelity model. Again, this is a gamble, but a challenge. We hope it works, and again, there are many papers being written as we speak, and the impression we have is that the approach is good. This one is a good one, and hopefully we can demonstrate a little bit at the end of the project.
Yeah. Then another similar question is that regarding the complexity of the new eVTOL aircraft. Guilherme Mom asked, pointed out that it's eVTOL are novel and complex, and he's asking if this approach has been applied already in simpler cases, like in airplane, for which classic solutions, test data and experience.
Ooh, that's a good one. Thank you very much. Yes, absolutely. You have a number of papers which we should have pointed out to them. I know that a notable example is the planning of space missions. There are 2 sessions at SciTech. You can look it up. It's about, I don't know the exact name. They use data fusion to estimate the performance of space vehicles in low orbit. I don't remember exactly the scope. It's NASA people, and there are 2. It's about the uncertainty quantification of this approach, and there are 2 sessions at SciTech, and they compare low fidelity with high fidelity with flight test. So you have the complete very good assessment of how good this method works for more conventional physics. Okay, it's not absolutely conventional, but it doesn't have a lot of studies. And so yes, there are some studies. There are some very nice studies. They are relatively young, and there are not too many around, but there are some of them. And I should have pointed out, and I didn't. I'm sorry.
Then we have another interested question, anonymous one, which is can a machine learning based model be acceptable for
Mission compliance.
so compliance to components of the station for a complete eVTOL for intern extrapolation from flight test covered condition?
Good question.
This was my last question in the list of questions I had for the conclusion. I didn't address it, but it's a very good question. No, I think we have, but in the principle, it is similar to the problem we have with simulation in general.
Yeah.
Except that your modelization techniques is new for us, and in this case, we will have to support to develop new means of compliance, or new means of compliance, or acceptable means of compliance, or guidance material, in order to accept or to reject the approach. But we have a limited experience at the moment.
Yeah. That was a.
But it's a very valid question. Again, it was the last one I wanted to address to you.
Speaking.
How to certify.
Speaking as
when artificial intelligence has been developed as a means of compliance, or to support the means of compliance.
As a CVE, which I sometimes also do, if I receive a report based on machine learning, I would check the content of the report extremely carefully before signing it off, and but really, really carefully. And whereas those on CFD, very familiar with, so I tend to be very lenient. Whereas someone sends me something based on data fusion, I will scrutinize every word, challenge every word. That's.
So the difficulty is whether it's a deviation from the physics, no? To understand if the uncertainty quantification is properly prepared.
Yeah, absolutely. Absolutely. So I will, for instance, try to estimate the uncertainties associated with the process itself. Yes, absolutely. Not easy. Not easy at the present stage.
You say Gaussian modeling is more critical than a neural network, for example?
Well, critical in what respect?
Would you scrutinize it with more care, or are they?
The other way around. Gaussian processes are very well known. They're simpler, and they have, in my view, they could have less bad surprises. And as the person here pointed out, there is some non-deterministic elements there, so one has to be careful with them. But they are almost conventional. They're well known. They've been well known for a number of years.
Yeah. Regarding uncertainty, Professor Quaranta is asking about example one. How did you assess the uncertainty there? If it's related to a numerical model uncertainty or to experimental uncertainty?
Yeah, thank you very much. It's a legitimate question. I normally here distinguish between the uncertainties associated with the process itself, so it's called epistemic, and the uncertainties associated with not knowing exactly the system, so the aleatory uncertainties. Now, about the first one, the epistemic uncertainties, you can build your well, if you work with code rigging, then you have an estimate of the your result comes with a confidence interval. So you have the mean value and you have a confidence interval. So you can you have an idea. So again, GP Gaussian process, so quantities are distributed according to Gaussian curves, and everything is expressed as a Gaussian quantity. So you have, again, you can fix your 1 sigma confidence interval, 2 sigma, 3 sigma, whatever, and this is a byproduct. So you have it. So you have an idea, and it's relatively simple, and it's a simple framework, and the information you have from there is that in this case, for instance, you see this confidence interval plus minus 1 sigma is a little bit bigger at the end at angle of attack 11. Everywhere else is small, and it gives you an indication. So it means that the data fusion process is very reliable, or no, it is not there. That epistemic uncertainty is associated with data fusion itself. Now, about all the other sources of uncertainties, then you have there are a number of approaches which are available, and my claim here is that if your low fidelity or if your multi-fidelity model is fast enough, then you can exploit a framework which we might call Monte Carlo. You don't do Monte Carlo; it's too expensive, but you can work with process or methods such as polynomial chaos, and you can run your analysis against one or a number of quantities of interest. At flutter speed, you can calculate flutter speed a number of times, and you vary at each time. You vary the random variable you're interested in. So if there is, I don't know, I'm not sure how realistic it is, you can carry out your flutter speed assessment varying slightly the material properties. So you're not too sure about the material property, and so you vary a little. You vary, for instance, the Young models a little bit, plus minus 1%, and you carry out you sample n different values for the property or properties, and then you carry out your flutter analysis n times. And if you do that, you exploit again polynomial chaos, for instance, or you do n equals 1000, and you do your Monte Carlo analysis, and you have some statistical analysis. And my claim here is simply that a faster model allows you to look into this and to obtain some statistics. And it doesn't go beyond this. So, well, actually, there are two claims. One is that the data fusion process can provide you with byproducts, an order of magnitude to the uncertainty inside the process, or the epistemic uncertainty, and then about the random variables you might identify in your system. Then a fast model allows you to look. So again, polynomial chaos can be one of the good approaches. It's computationally efficient. And again, feel free to disagree or reply to this answer.
Then always, let's say, regarding maybe polymy, but it's not asked from polymy, of course. Guillermo is asking if ROX is related to this, so the rotorcraft certification by simulation is related to this project. See if this project are related.
Believe officially there is no official link. There is an informal connection in that people know each other, and there is, I believe, you please correct me, EASA is interested, at least informally, in more than informally.
Well, ROX is supported by us, yes.
So ROX is supported officially by EASA. So EASA is the common denominator in the two. So,
but ROX is more focusing on flight tests and simulation, as implied by the title, and here we're more looking at aerodynamics and structural and interaction between it. So the focus is different.
Focus is different, but the how do you say, the
challenges
challenges are comparable, surely, and the connection between the two is EASA, the strong interest you have in these topics.
Our colleagues have involved us or keep us aware of the ROX project, and we invited our colleague involved here to this workshop.
Okay, then The next one is always by this Guilherme is asking regarding M&S credibility, which I guess stands for modeling simulation, or
Probably.
probably.
Okay, ASME holds several,
yeah. ASME holds several VV and UK subcommittees, including ML, CFD, solid mechanics. Where these references?
No, thank you. Partially, I think he hasn't asked me. No, thank you. No, thank you very much. No, only partially, and we'll make sure that they are taken into account. Thank you very much.
Okay, and then at least from Slido, there are a couple of questions from Dirk Davershot. I hope I pronounced it correctly. And he's asking about the execution time. And he's referring, I guess, to the low fidelity. If I'm not wrong, he was asking those questions during the low fidelity part.
Okay.
He's asking, when you mention execution time, do you mean processing time per flight hour?
No, per event. I meant the time which is necessary to complete the analysis of one flight event. So, for instance, you can quantify the time necessary to complete the analysis of a gas encounter. And the low fidelity is measured in seconds or minutes. And high fidelity, it is measured in hours or maybe days, depending on the model. Now, I'm referring to one single event, one single occurrence.
Then another one is always asking about the execution time. If is execution time a requirement for this project? For example, runtime per flight hours.
Yeah, that's a good. That's another good one. Shall we consider in this project in the typical certification process in which computational power is limited? In practice it is, and I believe, in my opinion, even large corporations with access to large clusters, in practice, you don't submit jobs which last 10 months. It's not very convenient. So I believe that the computational cost per event is relevant here. So yes, can you go back to the question exactly? Execution time requirement for this project, runtime per flight hour. I would say so. Yes, absolutely. But this is, I believe that it's also an important outcome of the project, how expensive it is. And the typical question, or the classical question, is now you're telling us, or the criticism that Elena and Laurent may have here is that you're telling us machine learning, and you're telling us that through machine learning you can reduce the number of CFD simulation. But what about training? Well, how expensive is training? And if it turns out at the end of the analysis that the CFD simulations you run in order to train your machine learning model are more expensive than the CFD analysis you need for certification, then you lost your bet. So yes, absolutely, it is. I believe it is a very important outcome.
Okay. Then from our colleagues in Vintatur, we have Dr. Capone that wants to add something on the rocks. Can you give him the floor?
Yeah.
He's unmuted. You have the floor.
Thank you. No, nothing special. I mean, I just want to intervene before to say that of course, ROCS is a different project with respect to ours. It's funded from a different entity. but we are in strict contact with the people of ROX, especially Giuseppe Quaranta, that is a colleague and a friend, and we also are collaborating in a new call together with the same people. Like, I mean, I look into the chat and I see people from this effort. I can see Langa Eliu, I can see Giuseppe Quaranta, Pierangelo Maserati, and so on. That's the only thing I wanted to add. Nothing else.
Thank you.
Okay, thank you. Do we have, I think, on slide itself, we have, we went through all the questions. If any of you have some additional question, let's say live in a more normal way.
Do you have any other
Maybe you guys
questions you'd
might
like to
have
ask? Something we mentioned this morning spoke is how can people, interested people, become involved in?
This was the last question I wanted to address.
Sorry.
No, but do. But basically, yes, we can not conclude, but one of the objectives also of this session is also to see if there is some either applicant or organization which can be interested to contribute or to feed this system and to try to collaborate in order to progress in this area. It's just the question, but then after we do not have a very specific frame to do that at the EASA level, but it is one objective is to generate a little bit of synergy in this area, and it means that if any people, any organization or expert want to share or want to try to contribute to this research and to investigate, I think they are welcome. But
absolutely.
Sorry, may I add
we
one
are.
Sorry, Marcello, since the time is running, I also would like to remind people that are in remote that when this session doesn't end the possibility to give your feedback to us. So please write to us an email, a message, or something. And if you have, sometimes what happens is that you digest something later on and you come up with a more, let's say, with a question or with a suggestion, and we are welcome all of this. So please do not hesitate to write to us. You have all the point of contacts in the call. Thank you very much.
Good. So please write an email to Pierluigi, not to me. I don't read emails. No. Please feel free, and especially if you have a case study to propose, that will be very useful. So we're looking into a proper case study to go through everything in the code. So we have to. And if we have more than one practical opportunity, we'll look into that with great interest. So again, feel free to get in touch if you believe this information can be useful, or the literature, the outcome of the literature survey, or if you want to drive us in a different direction. Yes. So absolutely, feel free, and if you have a practical case to submit to us, then as well, we'll be very interested as well. So thank you very much.
I don't see any hands raised or any comments on the chat. So on the note that all the attendees are actually very welcome to contact us and give all the input that was mentioned by Laurent and by Marcello. If there is really no more questions, I think we are very well on time, and I would like to thank on behalf of the whole project team for your attendance and for the participation and the questions. And I think during the project, we'll have more opportunities to organize project status workshops, consultation workshops, and we hope that we can count on you also to attend those.
Absolutely.
Yeah, definitely.
So
thank you, and I wish you a very good afternoon.
Thank you very much.
Thank you very much.
Thank you. Bye-bye.
Bye-bye.